Hello everybody, this is paper 1 from May 2024, and this is time zone 1. Let's have a look and see what we can do. Here we go. Starting off with a statistics question. The following data show the heights in meters of 6 players in a basketball team. And then here we have the heights. Part A asks us, for these 6 players, find the mean height, the median height, the modal height, and the range of the heights. So kind of a straightforward question to begin with, by and large. One thing to keep in mind, this is 6 marks. There are 6 marks here. So if there's only 4 questions, chances are at least some of these are going to require some process. And it doesn't exactly say where, so I think just by and large, let's try to show process where we can. Alright, so part A, number 1. Let's get started. For these 6 players, find the mean height. Remember the formula for the mean? X bar, the mean, is equal to the sum of all the individual values. So x1 plus x2 plus all the way up to the nth value. And this is going to be over, n, the total number of values. So in this case, what's the mean here? Well, the mean is going to be 1.67 plus 1.60 and so on. We're just adding up all of these different heights. 2.31 plus 2.31 plus 2.19, and then we're writing this all over. They told us there were 6 basketball players, so let's divide by 6. I'm going to go to the calculator screen and actually work this out. To be honest, we could actually find most of these values in spreadsheets, and maybe we'll do that at the end to check. But I'm going to go to the calculator screen right now and work this out. Okay, so let's get a fraction. And here we are, 1.67, and so on. 0.6, 1.68. I guess we could do 2.31 times 2, but here we are. Plus 2.19. And this is divided by 6. Everything looks good. Okay, so the average height is 1.96, and that seems to make sense. Alright, let's go back to the document here. So 1.96 meters. The median height, this is part 2. Let's go here. The median height I think is actually potentially arguably maybe a little more challenging. Remember, the median is the middle value, and since we have 6 values here, that might get a little more complicated potentially. So if we want to find the median, remember we can't actually do this with our calculator, but if we wanted to do this by hand, we could organize these values from the lowest to highest. So 160.167 is the second value right here. 168. And then it looks like it is 2.19. And then these 2 tallest players right here, 2.31. So the median, remember, is the balance point in some ways. It's the dividing, I guess, the point at which we divide our data set in exactly 2 halves. And here, since we have an even number of values, it's actually the dividing line is between 2 values. And in that case, what we would do is we would take the average of these 2 middle values. So in this case, the average, since it's not one or the other, it's the average of these 2, we could write as 1.68. Maybe I'll just change this and write an equation in some ways. The median is equal to 1.68 plus 2.19, and then this is divided by 2. And I'm actually just going to work that out on the calculator that I have beside me here. So 1.68 plus 2.19, I'm going to divide that by 2. All right. And here is the median, 1.935. If we wanted to write this to 3 sig figs, it would be 1.94. All right, good so far. Let's go on to part 3, the modal height. I'm actually going to write it up here instead of linearly, just so we can see the value. Modal, remember when you think modal, or when you hear the word, think most, the most common value. In this case, 2.31. 2.31 appears twice, and to be honest, we can't show a lot of process for that, so let's write 2.31 there. And last one is the range. I'm going to go ahead and erase this. The range, yeah, I'll write it down. I'll write it down here, I guess. The range. So when we're talking about the range, we're talking about, this isn't in the formula booklet, but we're talking about the distance from the max to the min. So if you find the shortest distance and you want to go all the way up to the largest distance, how far would you need to travel? In this case, our max is 2.31 and our lowest value is 1.60. So 2.31 minus 1.60, and that would be, let me just check again, yeah, and that would be our min. And so in this case, it looks like it would be 2.31 minus, this is going to be 0.71. That is our range. All right, and I think that is good. Before we get to that, let's just say, 6-mark question, roughly 6 minutes. How could we potentially do this really quick with the calculator to check some of these values? Let's go to the calculator for a sec. Here we are. If we wanted to, essentially this is just one variable statistics. So if we put these values in, that 1.67 and so on, we could put in all the heights, and this would be a decent way to check the values. Let's just make sure they're all okay here. Good, good, good. All right, let's just do some quick one variable statistics. Put our value in x. All right, x bar 1.96, that checks out. Our median 1.935, that checks out as well. And I don't think this gives us the range. No, it doesn't. Okay, great. Let's go back to the document. All right. Last question. A new player, George, joins the team. Their height is measured as 1.98 meters to the nearest centimeter. All right. Write down the shortest possible height of George. So 1.98 meters to the nearest centimeter. So this is essentially a number sense question or a rounding question. Write down the shortest possible distance. I guess I'll write it down here. So this is part B, if there's enough space. So George is 1.98 meters. 1.98 meters. And we want to find the shortest possible height of this individual basketball player. So we know, I'm running out of space here, but we know that 1 meter is equivalent to 100 centimeters. So if George is 1.98 meters, she is, or he is, 198 centimeters. But their height is measured to the nearest centimeter. So just like the question is, I suppose, what is the shortest possible height? If George was, for example, 1.979 and we're rounding to the nearest centimeter, then yeah, she would be 198. But what is the shortest possible height that George could be? Well, we know that if we have, for example, 197 point, and then what could it be? If it's 7, then obviously we're rounding up. If it's 6, we're rounding up. Anything above 5, and above, we round up to 198. So what is the shortest possible, I guess, height of this basketball player? 197.5 in this case. Anything lower, we would actually round down because that's the nearest. And 0.5 and above, we would round up. Okay. All right. I think we're good. Okay. Part 2, or question 2 rather, is a probability question, a nice kind of Venn diagram question here. Let's have a read. A teacher surveys their students to find out if they have eaten at the local Thai and Indian cafes. The results of the survey are shown in the following diagram. So here's the Thai cafe, there's everyone that ate there. There's the Indian cafe, and some people actually ate at both cafes, and some people didn't eat it either. So they told us there are Actually, they didn't tell us how many students there are, but if we add all of these up, we should be able to find it. Alright, so let's go ahead and have a read. Total of 6 marks. Write down the number of students surveyed. So I guess that's the first question. That's actually what you would want to know if you want to start doing some probability. Total number of students surveyed. Well, let's just add them up. Should we write it? Let's write it here in the margins, I suppose. Total number of students surveyed. Well, it's going to be 10 plus 13 plus 8 plus 2. And altogether, what is this equal to? Looks like it equals to 33. So remember, we're adding up all of these individual values. So 8 plus 2 is 10, plus another 20, plus these 13 here. So there's 33 people. Okay. Write down the number of students who have not eaten at the Indian cafe. So maybe I'll use the highlighter here, for example. If we wanted to say how many people have eaten at the Indian cafe, it would be everyone within here. These are the people that have eaten at the Indian cafe. But how many people have not? Well, everyone here outside of the Indian cafe, they haven't. And then, of course, even the people that haven't eaten at all, like these people, they haven't eaten at either of these cafes, but of course they haven't eaten at the Indian cafe either. So the number of people that haven't eaten at the Indian cafe is just, well, the 10 that just ate at the Thai and the 2 that didn't eat it either. So that would be 12. Okay. A student is chosen at random from those surveyed. Find the probability this student has eaten at both the Thai cafe and the Indian cafe. Alright. So I think I might actually use a little more space below to write this out. So here we are with part C. So we want both. And let's call, I guess, T the Thai cafe, and let's call I the Indian cafe. So we're looking for the probability that someone ate at both the Thai and the Indian cafe. And this, actually don't need this kind of notation, I'd imagine, for a 1-mark question, but sometimes this comes up, and it actually looks like it's coming up here, this set notation later on. This means the intersection, or we can read this as and. So how many ate at both the Thai and the Indian cafe? Well, that would be this area in the middle right here. These are, these are the individuals that ate at both the Thai and the Indian cafe. Alright, so what is in the overlap? There are 13 out of the total of 33 individuals. So remember, probability, desired outcomes over total number of outcomes. In this case, we see 13 individuals out of the total 33. Alright, so here we are further on. Let T be the event a student has eaten at the Thai cafe. Let I be the event a student has eaten at the Indian cafe. And here we are, actually, a decent set notation question here. Find, and then what does this mean? The probability that someone has eaten at both the Thai, or, this is the union, or the Indian cafe. So just to draw that again, this is our or. Actually, it's either or, so they can have eaten at either the Indian or the Thai cafe. So let's go ahead and write that up. D, probability that someone ate at the Thai or the Indian cafe. So this is anyone that is in either of these. So anyone in here or in here, in this case. This 10, this 13, and this 8. This would be the overlap of all of these. Essentially, all of these people have eaten at either the Thai or the Indian. What does that come out to? Well, it's everyone except for these 2 people on the outside. Those are the only ones that haven't. So it's 31 out of 33. Alright, just once again to kind of maybe just summarize. I hope that's a square. There we go. So if we're talking about, let's say, T and I, or just the overlap of A and B more generally, the overlap is just going to be this section because this is the and. And if we're talking about the or, for example, or is the easier case to satisfy. You just need to find the individuals that have eaten at one or the other. I should probably label this T, T, and I. And in that case, who has eaten at one or the other? Well, these people have eaten at both. These people have eaten at least at one of these. And the Indian cafe, these people would have eaten at the Indian cafe. So this right here is Thai or Indian. Essentially it's asking who has eaten at least at one of these, at either the Indian or the Thai, or even at both. That's the easier condition to satisfy. Alright, last one is part E. State whether the events T and I are mutually exclusive, and then justify the answer. Okay, so this one, I remember I used to think these were much more complicated than they really were. Thinking that, okay, I need to draw on some kind of like complex set notation or theory, but not really necessary. Mutually exclusive, what is mutually exclusive? It essentially asks, can these two events happen at the same time, or is it impossible for them to happen at the same time? So in this case, can someone eat at both the Thai and the Indian restaurant at the same time? Or is it possible for someone to have eaten at both the Thai and the Indian restaurant? And the answer is, yeah, we see that indeed has happened. We see these 13 people, for example, have eaten at the Thai and the Indian cafe. So the event eating at Thai cafe and the event eating at Indian cafe are not mutually exclusive. One could have, and these 13 people have done this, one could be in both of these events. One could have eaten at both of these. So what we could say, are these events mutually exclusive? We say no. No, they aren't. Why? Is because we see an overlap. There's an overlap in sets. Or we could just say overlap. Overlap in sets. Another way we could say it is P, the probability of T and Indian, does not equal 0. So we do have some people that have been able to eat at both the Thai and Indian cafe. In this case, there is a set of individuals that belong to both sets. Mutually exclusive, they would be separate, completely separate. To give you just an example of what mutually exclusive would be, maybe one of the most straightforward ones is drawing a heart and drawing a spade, for example. So if you have 52 decks in a card, if you look at, let's just take maybe 2 situations. There's one and there's the other. So this is what mutually exclusive means. Let's take one event of drawing a heart and let's say a 10. And if we have, what is it? I think it's 52 playing cards, 13, 26, yeah, 52 playing cards. We'd say, is it possible to draw both a heart and a 10? Yeah, it is. You can draw both a heart and a 10. These events are not mutually exclusive. So we would say not mutually exclusive. Why? Because there's an overlap. It's possible to do both. It's possible to get a heart and a 10. But what about this idea of, let's say, a spade? How does a spade look? Something like that. Is it possible to have a spade and a heart? And I guess I'm going to have to redraw this. No. Spades and heart. Let me get one color. It's a little too much going on here, I think. Hearts and spades do not have any overlap. It's not possible to have both of these events occur at the same time. I can reach into a hat and draw a 10 and a heart. That's not impossible. but I can't reach into the card and at the same time, well, I can't get a heart and a spade. So mutually exclusive means there's no overlap. This is P, let's say heart and 10, for example, equals 0. That's how we know it is mutually exclusive, because one and the other cannot happen. It's impossible. And that's mutually exclusive. In this case, well, they can both happen at the same time. There's an overlap. That's all we would need. Either of these will work. Either of these explanations. There's an overlap, or this right here. Alright, question 3, 7 marks. On January 1st, 2025, the Faber car company will release a new car to global markets. The company expects to sell 40 cars in January 2025. The number of cars sold each month can be modeled by a geometric sequence where R equals 1.1. Use this model to find the number of cars that will be sold in December 2025. So, what do we know? We know that the company expects to sell 40 cars in January. So in the first month, they're going to sell 40 cars. And then each month after is 1.1 times as much, or 10% more, I suppose. So they're asking us to use this model to find the number of cars sold in 2025 December. All right, not too bad. So let's go here, part A. How can we possibly solve this? I guess we could just keep multiplying by 1.15 12 times, but since they tell us, for example, that this is a geometric sequence, we might be, well, I think we would be better off just using the geometric sequence formula. So actually I'll write it out here. UN, remember this is the term value, is equal to the value of the first term times R, the common ratio, what we multiply by to go from one term to the next. And this is n minus 1. And if you're wondering, this is given to us in the formula booklet. I think it's under, I believe, number and algebra. Yeah, here it is. So this 1.3 right here, nth term of a geometric sequence, and then this is that formula right here. UN is equal to U1 multiplied by R raised to the power of n minus 1. Alright, so what are these things? I'm gonna, sometimes I wonder if this is maybe too much in terms of how drawn out it is, but if we draw a table, this is n, and then this is UN, the value. This is the first month we sell 40, and the second month, right, we multiply by 1.1. And what would this give us? 40 times 1.1, of course, 44, and so on, and so on, and so on. So if we want to go from one term to the next, it's, well, times 1.1 again. So this is R. This is our common ratio right here. So U1, the value of the first term, that's 40 cars sold, times R. R is what we multiply by to go from one term to the next. In this case, it is 1.1. U1 times 1.1, and then raised to the power of n minus 1. So in this case, what is n? Well, if January is the first month, the 12th month of the year is going to be December. So let's go 12 minus 1. And I'm going to head to the calculator screen now and work that out. So let's go and type in 40 times 1.1 raised to the power of, raised to the power of 12 minus 1. Okay, 114.125. Use this model to find the number of cars that will be sold. So let's go back to the document. 114.125. 3 sig figs is going to be 114 cars. Alright. Okay, I think that was pretty good. Let's go on. Question B, or part B. use this model to find the total number of cars that will be sold in the year 2025 and the total number of cars that will be sold in year 2026. So two questions here, 5 marks. Let's write this out. So just like we have a formula for the arithmetic sequence, we have a formula for a geometric sequence. Let's go to the formula booklet and check it out. Here we go, right here. So the sum of n terms in a geometric sequence, and they don't give us these, I guess we need to remember this is the value of the first term, this is r, the common ratio, n, how many, I guess, terms are we adding together, and this is once again r. Both of these are the exact same. This one and this one. If you're going to use your calculator, it doesn't really matter. The only thing is if r is bigger or smaller than 1, the common ratio, then it saves us from having to deal with negatives. But if you're going to use your calculator, to be honest, it's not a big deal. Either one is okay. Alright, so let's go ahead and write that out, and then we'll find those values. So sum of n terms is equal to the value of the first term multiplied by r n minus 1 over r minus 1. Okay, and let's find these values that we need. So if we want to find the sum, of the cars that were sold in 2025, we want to find the sum of the first 12 terms. So in this case, n is equal to 12. So over we see an n, let's substitute 12. U1, we know what that is. That's 40 cars were sold. I'm going to give myself just a little more room here. R is 1.1. That's that common ratio. N, we want to sum that first 12 terms. Minus 1. Here we go. And then it's 1.1 minus 1. Okay, I am going to head into the calculator screen now. Let's put that in. Calculator, set up a fraction. 40 times, and so on. Minus 1, and then 1.1 minus 1. Everything looks good. 855.371. Okay. I want to actually, let's go back to the document and write this out. 855.371, or to 3 sig figs, 855 cars. Alright, if we wanted to as well, so just to go back to the calculator for a sec, we can look at the various functions that we have. So if we click this button right here, we can see we have the sigma. So actually here it is. This is our sigma. And we can use sigma notation. And in this case, we're choosing our variable. And remember we used this un, and n was the variable, n was the term number that we could change if we wanted to find the first, second, third, fourth, fifth term and so. So we're using n, that's our variable. And what this is a capital Greek S, is a sigma. N is equal to 1. That's our starting point. And we say, okay, well, count from 1 all the way up to, we want to find the first 12 terms. And the calculator says, okay, I'll find the sum, the sigma, sum from the first to the 12 terms, and it says, what's the formula? And the formula is just that original formula. So how does the calculator know what the value of the first, second, third term is? Well, just use this 40 times 1.1 raised to the power of n minus 1. That was our geometric sequence formula. And that should give us the exact same value. So here it is once again, sigma notation. This is perfectly acceptable as well. The sum from the first term to the 12th, and this is the formula that tells us the value of each of the terms. Once again, to get there, right here, this little button. Okay, not too bad. And let's go on to part 2. So let's go back to the document here. Let me just label this. And here we go, part 2. All right, this one's a little more challenging. use this model to find the total number of cars that will be sold in 2026. So maybe I'll use this table. If we go down all the way, this is going to be the 12th year. And we know how many cars were sold in those 12 years. It was 855, roughly speaking. And the question is, okay, well, what about 2026? Everything before here, this is 2025. Anything after here is going to be, well, 2026. And 2026 would go up to, well, the 13th month, all the way up to the 24th month. Okay. So, how can we find this? I think there's two ways. The first way, actually I encourage you to stop for a second if you haven't already tried this one. Think about how you might solve this yourself. But the first way I think is if we want to use this formula again, this sum, is we already know the sum of the first 12 terms. So we can use this not to find the 13th to the 24th term, but we can, not directly at least, but we can use this to find the sum of the first 24 terms. That is to say the first 2 years. And if we know how much were sold in the first year, then we can just subtract that, and then we can find, well, the rest must be made up of this. What happened, or what we sold in the second year. So let's go ahead and do that. Let's try that method. So the sum of the first 24 terms is equal to, well, U1, we're drawing on this formula right here. U1, R is still 1.1, N in this case is 24, right? Both of these N's are the same, N and N. Minus 1 over, and this is R is again 1.1, minus 1. Okay, good. Let's go ahead and go back to the calculator. I'm actually going to copy this and use it again. And I'm just going to change this value to 24. Because that's all we're doing, really. Good. So, in the first 2 years, we sold 3,539.81 cars. So, if that's how many we sold within the first... Ooh. If that's how many cars we sold in the first 2 years, don't need that many digits. If we take away how many cars we sold just in the first year, then we'd have, well, the cars that we sold in the second year exclusively. So once again, sorry, maybe all these digits kind of maybe got in the way, but this is how many cars we sold after 2 years. This is how many cars we sold in the first year alone. So if we take, for example, number of cars sold after 2 years, take away the number of cars that we sold after just 1 year, that would give us, well, the portion that we sold in the second year. So let's go back to the document and write this out. So I'm going to actually write this out. So what can we say? So if we know that this was 3,539.89, if we take the sum of the first 2 years and take away the sum of the first year, then we'll have, well, just what we sold in 2026. So here we go. S24 minus S12 will give us, well, S12 to 24. Now I'm not going to write that. 3,539.89 minus 855. I'm just reading off the calculator what it said before. 2,684.52, or if we were to round up in this case, 2,685, or actually, sorry, let me just round to 3 sig figs. 2,680. All right, that is 3 sig figs. Remember, 1, 2, 3 significant figures. Okay, good. Let's go ahead and work this out in a different way with the calculator and sigma notation once again. So sigma notation is I think it's quite useful. I'm going to write it out once again. So here we are, sigma notation, n is our variable. Remember we said that this is our starting point? So we started above here. We said find the sum from the first to the 12th term, and this is our formula. Our formula is still the same. It's still going to be this 40 times 1.1 raised to the power of n minus 1. But we don't want to take the sum from just the first term to the 24th term. Sigma notation is a little more flexible in that we can say, hey, start at the 3rd term and take the sum from the 13th to the 24th term. And then we can put in the exact same formula that we had before. So here's our formula once again. 40 times 1.1, n minus 1 tells us the value of a term. We're telling the calculator, take the sum from the 13th to the 24th. And there it is. It gives us the exact same value in a different way. So we could have just written that. If you do choose this way, just make sure to write this out. This is your process, and then this is the value, of course. Last thing I kind of want to draw your attention to, here's the mark scheme. And where are we? This is it right here. So for some of these questions, I always think it's helpful, to put yourself in the best position possible, maximize process marks. Here it is, for example, 3a, attempts to substitute into geometric sequence formula for the 12th term. So attempt to substitute. They're even letting you, so if you want to find the 12th term, yeah, we could do that, 40 times 1.1 times 1.1. So even if you just started saying, I can multiply by 1.1, 1.1, you're showing that you understand something about geometric sequences. And to be honest, generous, or maybe it is somewhat generous in some ways, but it's process, it's understanding, and it just puts you in a better position, I think, to maximize your points and your score. And so a lot of different ways. Attempt to substitute into geometric sequence formula, not bad. Here again, attempt to substitute into geometric sequence formula, or just, attempting to multiply by 1.1 all the way there. These aren't the most efficient ways, but you can still get process here and there, which isn't bad, I don't think. Okay, let's go back to the document and continue on. All right, question 4, 7-mark question. A cell phone starts charging at 7 in the morning. While being charged, the percentage of power P in the phone is modeled by the function P is equal to 100 minus 60 times A to the power of negative T, where T is the number of hours after 7. Okay. Find the percentage of power in the phone at 7. So this is like classic question. Happens so often. Find the percentage of the power at 7. Essentially, well, when time is equal to 0, because T is the number of hours after 7. So when it is exactly 7, we know it's going to be T is equal to 0. So what percentage of power is left when T is equal to 0? I'm going to use I'm actually going to write this out down here. A. So our formula is P is equal to 100 minus 60 times A to the T. P is equal to 100 minus 60 times A to the negative T. And the question is, okay, well, when T is equal to 0, how much power is left? So let's go and put in T is equal to 0 and see what happens. 60 times A to the negative 0. And of course, anything raised to the power of 0 just becomes 1, actually. So what do we have? We have 100 minus 60 times 1, or 100 minus 60, and we're left with 40. So when T is equal to 0, P is equal to 40, and I think it's 40%, I suppose. It has the percentage of power in the phone at T is equal to 0 is just 40%. All right. The percentage of power in the phone reaches 75% at 8 o'clock. This is another kind of classic. There's so many of these questions where they ask you to find one unknown, or the initial starting value, where we raise some variable to the power of 0. And then they're going to give you two values, an x and y, or an input and an output, and we use it to find the other variable. So in this case, we want to find the value of a, this right here, and they're giving us some, well, inputs and outputs, I guess, some other known values. So percentage of power reaches 75%. P is equal to 75. When t is equal to, well, t is equal to 0 is the number of hours after 7. So this would be t is equal to 1, because it's 1 hour after 7. So let's go ahead and put that into our formula. So here we are for b. P is equal to 100 minus 60 times a to the negative t. We have this value where p is equal to 75. When t is equal to 1, p is equal to 75. When t is equal to 1. Okay, there we go. T is equal to 1. Everything looks good. Alright, after this, I have to do a little bit of algebra, or, to be honest, let's just end solve as well. Let's go to the calculator then. I'm going to clear our screen just because I should get a whole new document. It's getting a little cluttered. Here we go. Menu, algebra, numerical solve. 75 is equal to 100 minus 60 times a to the negative 1. And let's ask the calculator to solve for a. A is equal to 2.4. Okay, let's go back to the document. Write that out. In this case, a is equal to 2.4. Okay, good. Remember, both of these are 2-mark questions, so you want to show some process. Draw the graph of p is equal to 60 minus 60, sorry, p is equal to 100 minus 60 times a to the negative t on the following set of axes. 2 marks. So 2 marks, we don't have too much time for this, or, I mean, in terms of what we can possibly do to make this accurate. 2 different things. We know that, going down here, we have t is equal to 0 when p is equal to 40. So when t is equal to 0, p is equal to 40. We know this point. I'm going to write it out in blue. Right, this is 0 and 40. We also know that when t is equal to 1, p is equal to 75. So we have another point. And to be honest, we could actually look at this function itself and try to see what else is going on. So we have, for example, 100 minus, and then 60 times a to the negative t. We can potentially look at this a little more. This a to the negative t, remember, anything to, if it was just a to the negative 1, it would be 1 over a. This a to the negative t actually means that we have 1 over a to the t. Say, okay, what is the point of this? What is the point of this? If we rewrite this thing, this 100 minus 60 times a to the negative t, we could rewrite this as 100 is 60 times 1 over a to the t, or, and I hope this isn't too drawn out, over a to the t. And what does that mean? Well, if a itself was equal to 2.4, which we found out it was, 2.4 raised to the power of t, we're taking some value of 60 and we're dividing it by 2.4, some larger and larger and larger value. So we have 100 minus some larger, 60 divided by 2.4t. So this 60 is being divided by a larger and larger and larger number. So it is getting smaller and smaller and smaller. And then we're just left with 100, essentially. So we kind of found the end point first, but it means we're going to get closer and closer to 100 as we go through. 100, and we're taking away, so 60 60 over 2.4, for example, and then 60 over 2.4 to the 2, right? It's going to be 60 is being divided by a smaller number. So we're taking less and less and less away. And then this 100 is going to get, well, there's going to be more of it left over because we're taking less and less away with this as time goes on. Okay, I think we can actually use some of that theory for later on, but how do we fill this out further on? I would say, I hope that wasn't too long-winded. Two different things. We can graph it, or we can just find some other values. Here's our function. P is equal to 100 minus 60, and we found out what A was, 2.4t. So let's find some values for when t is equal to 3, and maybe when t is equal to 5. Let's do that, and let's plot those points. So here we go. Back to the calculator for a sec. 100 minus 60 times 2.4 raised to the power of 3. Okay, something went terribly wrong. Okay, of course. 100 minus 60 times 2.4 to the power of negative, it was negative t, remember? There we go. So when t is equal to 3, we have a value of 95. So I'm going to write that out here. T is equal to 3, p is equal to 95.66. T is equal to 3, we're at 95.66 or so. And what about when we're at 5? So let's go back to the calculator. And when t is equal to 5, let's change this variable. We're getting closer and closer to 100. So let's go back to the document. At this point, p is equal to 99.25. So once we're at 5, we get very, very close to 100. Not yet touching 100, but very, very close. Then we can plot a smooth curve. We could find the value of 2. Imagine it's going to be something like that. So I'm going to try to sketch this out, draw the graph on the following set of axes. So let's go through. I'll do my best here. Alright, not terrible. Okay, there it is, 2 marks. And let's, just for peace of mind, show you guys the mark scheme. Here we go. So what are they looking for? For correct general shape, increasing and concave up. And then these are the 2 points that we should know, right? The 0 and 40, times 0 is 40%. And then at time 1, it's 75%. And then finishing around 100, so it gets increasingly close to this, what's called a horizontal asymptote. Yeah, all right. So that's what they're looking for. Initial value, this other value that we know, and then approaching this horizontal asymptote and smooth curve, of course. All right, so let's go to part D, this final part of this question. State a mathematical reason why the model predicts the percentage of power in the phone will never reach 100%. So D, 1 mark question, mathematical reason. So we can't just say like the battery's old or something. Mathematical reason why the model predicts percentage of power will never reach 100. There's 2 ways. The easiest one I think is to say, hey, it looks like we've got this horizontal asymptote right here. And we could just say that there is an asymptote. An asymptote, remember, is a value that we approach but never reach. Asymptote at p equals 100. We're approaching this value of 100, but we're never going to reach it. That would be one. The other possible explanation is if we look at this formula once again, we have 100, and we're taking some value away from it. And if we were to rewrite this, knowing that we know that A is 2.4, We have 100, and we're taking 60 divided by 2.4 t. So even when t becomes like massive, massive, so let's even write an example out right here. Once we have 100 minus 60 over 2.4, let's imagine t is like, I don't know, maybe 50 or 100. Even if we have 60 divided by, let's say, 1,000,000, I mean, this is still some positive value. So 100, we're still taking away some positive value from this. So why do we never reach 100? Why? Because we are subtracting some positive value. Something like this. 100, subtracting 100, 100 minus a positive value, something like this. 100 minus positive value. So non-zero value, essentially. Cannot equal 100. Alright. Just one mark. Okay. Alright, let's go on. Here we go. Financial mathematics. Yeah, let's see this. So sometimes financial mathematics can seem like rather daunting, but once you get familiar with them, to be honest, they're very similar. They're by and large pretty similar, at least on a paper one. And sometimes it's reassuring seeing financial, because it's like I've seen all variations. Alright, let's give this a try. Man deposited 1,000 into a savings account with a nominal interest rate of I% compounded monthly. At the end of the 8th year, the amount in the account had increased to 150,000. Find the value of I. Okay, so putting some money into an account, we have the initial value, we know the final value, we know how many times it's compounded annually. We just need to find the interest rate, and we know that n, number of years, is equal to 8. Okay. Two different ways we can work this out. We can work this out using the financial solver or compound interest formula. I'll show you the compound interest formula here. It's actually right here, 1.4. It's nice because they give us these values. Present value, this is k, number of compounding periods, r is the percentage, the interest rate. So it's kind of nice. And FB is the future value. I think for these kind of questions, generally it's a decent idea, potentially at least, to use compound interest formula because it's not as hard to make an error. So here it is. Final value is equal to present value, 1 plus r, 100 times k, n times k. Final value we know is 150,000. Present value was 100,000. 1 plus the interest rate, we don't actually know yet. We know it was compounded 12 times a year, and we know the number of years was 8, and this is 12. I think that's it really. And after that, we'll end solve, and then I guess we're solving for I in this case. So let's go ahead and end solve this. Let's go to the document. I'm, to be honest, a little apprehensive because sometimes these don't actually work in end solve. The calculator has some difficulty. But let's give it a try this time. 150,000. Where's the equals button all of a sudden? There we are. 100,000. Alright. R, we don't actually know what this is. We called it I before. I is actually an important value in mathematics, so I'm actually just going to write it as R here. I don't want the calculator to potentially get confused. I don't know if it would, but 8 times 12. Okay. And then we have to say, what are we looking for? We're looking to find R. No solution found. I was hoping that wouldn't happen, but it does actually happen. To be honest, sometimes with these type of questions, I'm going to go ahead and see if it's because of that potentially, but I don't know. No solution found. Okay, so in this case we can do two things. We can either graph this as a function and then find out when it equals this 1,000 or 150,000, or we can quickly turn to the financial solver. I guess timed exam maybe for something like this. Yeah, the calculator does for some reason have difficulty finding the R in these kind of situations. So maybe that's an argument to use the financial solver. Yeah, potentially. Alright, let's go use the financial solver for this. Calculator is not being helpful on this, I suppose. Let's go and go to our finance. Okay, so interest rate is what we're trying to solve. The present value is the value that we started with. Remember, we say money flowing out, money flowing in, so money flowing out, as convention, we put a negative. It's leaving our pockets. Even though we still have it in the bank, it's leaving our pockets. PMT is 0. We're not making any payments, recurring payments. The final value, this is the money we have coming towards us at the end, is 150,000. Payments per year. For compound interest formula, when we just put a value in the account and just watch it grow, the PPY, payments per year, we keep the same as CPY, because essentially it means the idea that the bank is paying us 12 times a year, paying us installments on our interest 12 times a year. Alright, end payment at the end. So PPY, keep the same as CPY. CPY is 12 because the bank compounds the interest monthly, 12 times a year. Last one is N. We keep it in for 8 years, and it's compounded 12 times a year, so that's at 96. Interest rate we wanted to find. Payment was 0, we're not making any. And there we go, 5.08%. 5.08%. So let's go back to the document and write that out. So I is equal to 5.08. If you do choose to use nsolve, then remember you have to write out all the values, n, I, pv, and so on, because that's your process. Alright, let's continue on. Man withdraws the 150,000 and places it in an annuity. Alright, so it's some kind of pension fund. Earning a nominal annual interest rate of 6.1% compounded monthly. At the end of each month, man will receive a payment of $1,000. Find the amount of money remaining in the annuity at the end of 10 years. Express your answer to the nearest dollar. So a lot going on here. They want the answer in the end in terms of the nearest dollar. The amount that she's putting in the annuity is 150. Bank is giving us 6.1%. They're compounding it monthly. That happens at the end of the month, and we're getting payments of $1,000. Okay. And we want to find the amount of annuity at the end of 10 years. Okay, it's a good question. It's a pretty challenging question. All right, let's put those values for our financial solver. So what are we going to need? We're going to need N, I, PV, present value, payments, going to need final value, and then PPY, payments per year, and then also compounding per year, and then this last one is payment at, which is at the end. Okay, interest rate is always the easiest. Let's start with that one, 6.1. Okay, so present value, 150,000. We say this is money flowing out, so this one we're going to have to be careful with. $150,000 we're putting it into annuity. We don't have it no longer in our pocket. We gave it to the bank. It's still our money, but it's out of our pocket in some ways. The payments, however, this is PMT is recurring payments. So in this case, the payments of $1,000. This is actually money coming towards us. Man will receive, right? It's money coming towards us. She'll receive $1,000. We want to find how much will be left at the end of 10 years. So we actually want to find the final value. Payments per year. She will receive money, I think it said monthly, at the end of each month. So payments per year, she'll receive 12 payments every year. And the bank as well is going to compound this 12 times a year as well, CPY. All right. And then how long is this? Well, at the end of 10 years, we want to find the final value. So 10 times 12, 10 times 12, or we can just say total number of payments, that's what this n is 120. Okay, let's go ahead and put this in our calculator. 120 total payments. 6.1 payments is 1,000, flowing in the other direction. Final value, 1 and 0. 12, 12, end. Good. Alright, so she has $110,000, 866.7 and 70 cents, I guess, or 71 cents. So find your answer to the nearest dollar. So let's go and write this out. Going back to the document, the answer is final value 110,866.706, I guess. And to the nearest dollar, we would say that is 110,8667. So, okay, good. And I think we're okay. So nearest dollar we would round up. Yeah, even though at the end of 10 years, if she were to check her bank account, she would see that she has 70 cents or 71 cents, and to the nearest dollar we would round up. Okay, not bad. $110,000. We can ask ourselves if that makes sense. After 120 $1,000 payments, why does she still have so much? And we say, okay, maybe that seems a little strange. It's actually because she's earning a fair bit of interest. 6.1% on 150,000. Should be earning about, what can you say, maybe $10,000 a year, to be honest, in interest. And so taking out around this $12,000, that's not too bad. Her money doesn't evaporate. She's able to take out, 120 payments and support herself for 10 years. And that's why this number is realistic. All right, Voronoi, question 6. Here we go. Points A, 3, 4, B, 9, 6, and C, 11, 2, are shown on the following diagram, along with perpendicular bisectors of AB, AC, and BC. So these are the perpendicular bisectors. They run between, right? They bisect, that means cut exactly in half, B and C, or they cut, for example, A and C, or they cut A and B, so on. The perpendicular bisector of BC, that would be this line right here, intercepts the x-axis at coordinate 0, -1, and 2, 0. Write down the equation of the perpendicular bisector. So this is this perpendicular bisector. They want us to write down an equation just in terms of y equals mx plus b, it looks like. So let's see if we can do that. I'm going to actually write it out in this little margin. I think, to be honest, there might be enough space. So let's write it out. Let's write it out here. I don't like that there. Here we go. So we have y is equal to mx plus b. M, we know, is the slope, and b is, of course, the y-intercept. So do we have the y-intercept, the point in which we cut the y-axis, for example, right here? Where do we cut the y-axis? In this case, they tell us we cut the y-axis at this point of 0, -1. So we know that b is equal to -1. That's the y-intercept. The slope-intercept form tells you the y-intercept, and if we find the slope, we can find that other ingredient. So, I guess, why are we doing it this way instead of actually just, finding the midpoint, finding the slope between both lines, finding the perpendicular, and then substituting? Why are we not going through all that trouble? First off, it would take quite a while, and it's only a 2-mark question. If we actually needed to find the midpoint, and then the slope, and then the perpendicular, and then substitute, it would be at least 3, potentially 4 marks. 2 marks tells us that there's other ways. And using this idea of y equals mx plus b is one of those ways. So b is the y-intercept. It's -1. That's where we cut the y-axis. And the slope itself is, remember, m, which is rise over run. I think the easiest thing to do is sometimes draw triangles, actually. So if we start at, for example, this point right here, and we run for 2 units, how much do we rise? So let's find 2 points on the line, which is what we do when we calculate slope. And we say, okay, we rise for 1 for a run of 2. We start at 2, go up to 4, travel a distance of 2. So rise over run is rise of 1 for a run of 2. And that's just equal to 0.5. So there we go. 0.5 x minus 1. And that's our slope intercept form. That's our equation of a line. We know the slope just using rise over run, or just choosing 2 points if we want. And then our y-intercept where we cut the y-axis. Alright. Whoops, wish I could get that back. 0.5x. Let me just erase this. Okay, great. Okay, let's go on to the second part. The equation of the perpendicular bisector of AB. So where's that? Right here is y is equal to -3x plus 23. Find the coordinates of point V where the perpendicular bisectors meet. Give your answer to 4 significant figures. Okay. So for 4 significant figures, that's actually quite important. To be honest, we'd actually lose a mark if we didn't do that. It's a 2-mark question. So they tell us the perpendicular bisector of AB. So the perpendicular bisector of AB is this right here. And we just found the perpendicular bisector of BC right here. So let's maybe use this color is okay. Alright, and the question is, okay, well, where do they meet? If this is one of those perpendicular bisectors, 0.5x minus 1, and this is the other one, and its y is equal to -3x plus 23. If we were to call this y1 and this is y2, the question that we're kind of asking is, when does y1 equal y2? That's kind of the question that we're asking. Well, where do they equal each other? Where do they meet? Well, they meet at V, and that's exactly what we're trying to find. So what we could do is set up an equation. So let's go ahead and fill this out a little more. y1 is equal to -3x plus 23, and y2 is equal to 0.5x minus 1. So essentially they meet when they are equal to each other. That's where they intersect. Where is that one point where they have the same inputs and outputs, that same xy value? When does y1 equal y2? And when we substitute for those, we can actually create an equation. And after this, we're just looking for that x value. And for that, we can end solve. So let's go ahead and do that. Let's go to the calculator. I'm going to get a new window, actually. Okay. Menu. Let's go to add calculator. Menu. I'm thinking that maybe there's a quicker way actually in the back of my mind. Potentially. So negative 3x plus 23 is equal to 0.5x minus 1. Let's solve for x. Okay. Let's not do this. Let's not do this. So I was thinking, yeah, let's just set one equation equal to another. But I had forgotten about the 4 sig figs. And substituting this into one of these equations to find the y value, which we could do, could potentially be a little tedious. So I'm going to backtrack a little. Sorry about that. This way is, it's not a bad way to do it. We could find the x value, substitute into here, and then find the y. But if there are so many digits that we're going to need, maybe we just graph it. So let's graph negative 3x plus 23. And then let's graph the other one as well. 0.5x minus 1. Oops, that's not what we need. 0.5x minus 1. Okay. And then here we can find our intersection point. So menu, analyze graph, intersection. Let's highlight that area, and there it is again. If we're going to need 4 sig figs, let's just graph it. It's going to be easier. Okay, so let's go back to the document for a sec, and actually just reading it here, 6.8571. That's our x value, and this is our y value. So now let's go back to the document, and the coordinates to 4 sig figs will be 6.857, and the other is 2.42, and since it's 8.6, we're going to need to round to 4.29, so 4 significant figures. Okay. Last question, part C. A Voronoi diagram is constructed with points A, B, and C as the 3 sites. Draw clearly the edges of the Voronoi diagram on the given diagram. Okay, so those boundary points. Going to go ahead and clear this up because we don't need all of this. Okay, so where are those boundary points? So where's the boundary line? So Voronoi tells us, what does Voronoi tell us? So we have these different sites, right? This is one of the sites, this is one of the sites, one of the sites. And Voronoi divides a given coordinate grid into cells. And each of those cells, a point within each of those cells, would mark out the area that is closer to any one given site. So for example, if we're here, what is the site that we're closest to? Well, we're closest to C. If we're in here, what is the site we're closest to? Well, this is a perpendicular bisector, the line that divides B and C exactly in half. So anything on this side, we're closer to B. So we know this is one of those boundary lines that's going to be that kind of dividing line which distinguishes when we're closest to B, when we're closest to C, when we're closest to B, and so. So let's go ahead and actually don't know how to make this thicker, but let's write it out. And maybe we'll just give it a different color. Okay. Okay. So here we are. We'll draw it off twice. That doesn't help much. Anyways, here is the line that divides both C and B. We're on this side, we're closer to C. On this side, closer to B. Let's ask about this line. Do we need to do anything with this? Should we shade this, for example? Is this a boundary line? Well, not really. This line actually marks the separation point between C and A. That's that perpendicular bisector. But when we're here, we're still clearly closer to B. Here, we're still closer to B. It's only this perpendicular bisector between A and B that is going to be relevant. On this side, we're closer to B. This side, we're closer to A. So let's go ahead and mark that out as well. Okay, very good. And the same process here. So we've already got the boundary line between C and B, boundary line between B and A. What about between A and C? We said this boundary was between A and C. And here we're clearly on the side of C. Here we're clearly on the side of A. This is that boundary line that divides. This is, remember, the boundary line between A and B, so it's not relevant. And neither is this. This line is between B and C, and it's not relevant. It's actually only this line right here that's going to be important in determining which point is closest to which site. So any point within this, we're in this cell, we're closest to A. Here we're closest to B, and here we're closest to C. All right, draw clearly the edges on the Voronoi diagram of the Voronoi diagram on the given diagram. Okay, there it is. Okay, nice trig function question. I think these questions are kind of nice. Potentially a little challenging because we don't really have a formula for these. Not exactly. They don't give us a lot in the formula booklet for these. So that makes it a little challenging. But let's see what we can do. Here we are. The following graph shows the depth of water, d meters, in a river at t hours after 12 in the afternoon. At 15 hours, the depth of water reaches 7 meters, its highest level. So let me just look at the time scale here. So the depth of water, d meters in a river after 12. All right. T hours after 12. So if this is 0 after 12, this is 12 o'clock. At 15 hours, so 3 hours after 12, we reach a maximum of 7. So here's 7. Its highest level. At 21 hours, so this would be 9 hours. 9 hours later, the water drops to 1 meter, its lowest level. The depth of water can be modeled by the function, a sine function, dt a sine bt plus 4. So they give us one number already. Find the value of A, find the value of B, find the first time after 12 when the depth is equal to 3 meters. Give your answer to the nearest minute. 3-mark question. Okay. Here we go. Let's just put some values on here that we know. So time on the bottom, the scale here is t hours after 12. So 15 hours, that's going to be, well, t is equal to 3 because it's 3 hours after 12, and we know the height is equal to 7. So we know one thing. We know 3 hours, we have a height of 7. And at 21 hours, well, how far is that away from 12? It is 9 hours. 21 minus 12 is 9. And then the water is at 1. So right here we have another point. At 9 hours, we are at 1 meter. Okay, find the value of A. So A is what is called the amplitude. Essentially you can imagine A as the height of the wave in some sense. So if this is, let's say, the average, the midline in some sense, A is the height of the wave. That would be A right here. And so how do we find A? A is given by max minus min divided by 2. And that should make sense. If A, for example, is the distance from the midline to the peak, or the height of the wave, if we go all the way from the very highest point to the lowest point, or in this case, all the way from 7 to -1, well, that's going to be a distance of 6, but that's the distance from the highest to the lowest. We just want from the midline to the highest, so we divide by 2, which is going to be 6 over 2, which gives us 3. And that's exactly what we see. From 4 all the way up to 7, we travel a distance of 3. Alright, that is our amplitude. Find the value of B. B is a little more challenging to find. B, remember, is given by, B is, we'll use blue here, B is equal to the frequency, and that tells us how many cycles, any up-down cycles, any complete cycles we have within 360. So B is equal to 360 over the period. Essentially, how many cycles, this is, for example, well, this would be one complete cycle when we make it back to here. How many cycles are there within 360, I guess, units, we would say. In this case, hours. Alright, so usually they actually start us off by asking us to find the period. So 2 marks is a little low, I think, potentially. But here we go. Period, how long does it take to complete one complete cycle? So we start at 3 hours, and then 6 hours later, we've gone from the highest to lowest. We've gone from, well, we've gone half a cycle. So period, let me write that out here. Actually, let me just draw a quick diagram to show you exactly what period is. So if we're talking about some sine wave, for example, the period is the time taken to go one complete cycle. This is the period, for example. So, period, how long does it take to go one complete cycle? We start at 3, we go from the highest to the lowest in 6. It's going to take that exact amount of time to go back up to the top again. So period is equal to, I'm going to write this out here, right here, I guess. Period is equal to, well, 6 is one cycle, times 2 would give us a whole. So the period is just equal to 12. I hope that does make sense. Half cycle in 6, one complete cycle in 12. That allows us to find this value of B. If we can go one complete cycle in 12 hours, how many cycles can we fit into 360? Well, 12 goes into 360 30 times. Okay, so there it is. 360 divided by the period. Period is the time taken to complete one complete cycle. How many of these cycles can we fit into 360? We can fit in 30. So the value of B is equal to 30. Alright. Find the first time after 12 when the depth of water is equal to 3 meters. Give your answer to the nearest minute. Alright, so how can we do this? So why do they ask us to find these values of A and B? Well, because we have this function right here. The distance is, or sorry, the depth as a function of time is given by this. And we found those missing pieces of A and B. So we know that I'll use a different color, I guess. We know that the depth at time t is given by 3 sine B is equal to 30 t plus 4. Alright. And what they're asking us to do is find the first time after 12, so essentially after this point, when the depth is equal to 3 meters. So when the depth is equal to 3, or when dt is equal to 3. So let's go ahead and substitute 3. And here is our function. And essentially we're asking, what is the value of t that we can substitute into our function in order to have the output equal 3. So here's the depth, here's our function. Let's find that value of t that makes this true. And to do this, we could do a little algebra, to be honest. But I think going to potentially also end solve. But let's go to the calculator and work it out. Menu, algebra, numerical solve. 3 equals 3 sine 30t plus 4, and then we want to solve for t. One thing to keep in mind, make sure you're in degrees. Sometimes when you get set up and to press the test, you might see radian. Make sure you're in degrees here. 3 equals 3 sine 30t plus 4. Good. Alright, so this is maybe why it's 3-mark question potentially. But we get a negative value. So this is, when we use nsolve will find the value that is closest to 0. And we actually don't want a negative value because this is something at like 11. And the question asks us to find the first time after 12. So let's go use nsolve again. And let's specifically tell the calculator to find a value greater than 0. So let's set a lower bound. And in this case, the first value greater than 0 is 6.649. Okay. So, find the first time after 12 when the depth is equal to 3 meters. Give your answer to the nearest minute. So, what is the answer here? We know that t is equal to 6.649. Okay, t is equal to 6.649. That's 6 hours and 0.649 hours as well, right? Because 6 plus 0.649 is 6.649. But how many minutes is this? Well, 0.649 hours. We have 0.649 times 60 minutes, because we have 60 minutes in an hour. I'm going to work that out on my calculator here. 649 times 60. And this is going to be equal to 38.94. So 0.649. I don't want to draw this out too much, but what is this? It's essentially 64.9% of an hour times 60. That's how many minutes, of course, we would have. If we wanted to round this to the nearest minute, looks like it would be 6 hours and 38.94, oops, no, 38.94, this would be 39 minutes. Hopefully not too crunched. Alright, not too bad. Alright, 6 hours and 39 minutes. Find the time after 12 o'clock when the depth is equal to, well, 6 hours and 39 minutes after. Okay. Okay, I think that's good. Let's do another question. What do we have here? Okay, maybe last. No, let's try this one here. 6-mark question, moving along. The formula F equals 1.8C plus 32 is used to convert a temperature in degrees Celsius C to degrees Fahrenheit F. Find a formula for converting a temperature in degrees Fahrenheit to degrees Celsius. Alright, so this is somewhat of a rare question for applications interpretations, potentially at least, because it's asking us to do some specific algebraic manipulation. Maybe it's not so rare, but in some ways it's not as common as some of the others, I suppose. So, what are we asked to do? We want to find a formula for converting temperature in degrees Fahrenheit to degrees Celsius. Right now we put in C, some value of Celsius, and it gives us Fahrenheit. We want to find a way where we can convert Fahrenheit into Celsius, for temperature degrees Fahrenheit to Celsius. So, right now we've got this. Fahrenheit is equal to 1.8 C plus 32. We want to find a way to get C all by itself and, well, input Fahrenheit. So, what can we do? We're going to need to get C all by itself. And to do this, we have to draw on some of your earlier algebra skills. So, let's get C all by itself. First thing, use order of operations. Take away 32 from both sides. 32 minus 32 goes to 0. What do we have now? We have F minus 32 is equal to 1.8C. We want just C all by itself. We don't want 1.8C let's divide both sides by 1.8. Anything divided by itself is just going to be 1. 1.8 divided by 1.8 is just 1. So now we have C is equal to F minus 32 over 1.8. I'm going to rearrange this. It means the exact same thing. I think it just looks potentially a little nicer. F minus 32 over 1.8. Alright, so there we are. We have to get C all by itself by using what are called inverse operations. Just want to show you the mark scheme for a sec. Here it is, 8a. Instead of just like leaving this, I'd say never leave a question exactly. Attempt to rearrange and isolate C. So subtracting 32, dividing both sides by 1.8. So even if there's some kind of understanding in terms of how to manipulate this algebraically, you will get some method marks. And never leave, I don't think, method marks kind of just lying there. Alright, let's go back to the document. Okay. So that was for A1. Let's go to part 2. Find the temperature in degrees Celsius that is recorded at 77 degrees Fahrenheit. So when F equals 77, C is equal to what? Okay. So here's our formula. Let's move this down just a little. C is equal to, F is equal to 77 minus 32 divided by 1.8. Alright, I am going to work this out on the smaller calculator that I have right here. 77 minus 32 divided by 1.8. And it just gives us 25 degrees. 25 degrees. Remember, order of operations, do the top first. Okay. Part B, let's go on. Over 1 year, the mean daily temperature in Mexico City was calculated to be 17 degrees Celsius with a standard deviation of 9 degrees Celsius. All right. For the same year, find in degrees Fahrenheit the mean daily temperature in Mexico City and the standard deviation of the daily temperature in Mexico City. Okay, so remember we've got like this, whoops, something like this, standard normal curve, and it's symmetrical about the mean, and this is X bar, and in this case the mean daily temperature of Mexico City is 17, and then we've got this standard deviation, right, which we give this sigma, and in this case sigma is equal to 9, so they're both the same. So what is the mean daily temperature of Mexico City? Well, if the average was 17 degrees C, we can actually just, let's see, it have to be 7 degrees Celsius. For the same year, find in degrees Fahrenheit. So we've got some formula right here where we can plug in some value of C and it'll tell us the value of Fahrenheit. So in this case, we don't really need to overthink this one too much. So this is B1 rather. In this case, if our formula F equals 1.8 C plus 32, if we know that C is equal to 17, we just need to find Fahrenheit, we can just plug in a value of 17 into our formula to convert Celsius to Fahrenheit. So I'm going to work that out. 1.8 times 17 plus 32. Oops, plus 32. So it would be 62.6 degrees Fahrenheit. And then we can write degrees Fahrenheit. I should have written Celsius here actually as well. Alright, not bad. The standard deviation of the daily temperature in Mexico City. So if the standard deviation is 9 degrees Celsius, what is it in Fahrenheit? And this is actually the trickier of the two questions. So you might think, okay, well, for this one we just inputted 17. So why don't we just input 9 here? 1.8 times 9 plus 32. And what we'd find is we'd find that the variation would be something like 40, I don't know, something like 42 maybe degrees Fahrenheit or something, which is pretty massive, and if we know, if you have some kind of sense of like degrees Fahrenheit, this would be a rather large variation, especially compared to the mean. So what is going on here? In this case, we wouldn't take this plus 32. We would just use this scale factor of 1.8. So for the standard deviation, for part B, we would say, well, the standard deviation of 9, and we would just multiply it by that scale factor of 1.8 in this case. So 9 times 1.8, and this would give us 16.2. So another way to potentially possibly think about this, so why don't we have this plus 32? Why is it not factoring into this conversion? I think if we imagine using this scale, once again, this kind of standard deviation, let's imagine that the mean temperature was, again, let's say 17. So the mean temperature is 17 degrees Celsius, and we know as Fahrenheit that's equal to 62.6. 62.6 degrees Fahrenheit, and this is Celsius. And that's our mean, that's x bar. All right. So we can have this equivalence in some ways. And then we say, okay, well, the standard deviation is constant. Or sorry, not constant. Let's imagine it's 0. It's unlikely that the temperature wouldn't change, but let's just imagine, for example, that there is absolutely 0 variation in temperature, or 0 variation in any kind of whatever kind of, what can we say, whatever we're studying in this case. But let's imagine it's temperature. So if there's 0 variation, 0 standard deviation, that means that, well, all of the values are actually centered at this one value, and our standard deviation, if our standard deviation is 0, we can't imagine, for example, putting 0 into this function and still saying, hey, our variation is 32. The variation itself would be 0. We would just multiply that value by this scale factor of 1.8. So imagine, for example, standard deviation is equal to 0. All values are constant. If someone says our standard deviation is 0, we would multiply that standard deviation by the scale factor of 1.8, but we wouldn't suddenly add 32, add some value, because the standard deviation just tells us how spread out the values are. So we would multiply it by this 1.8, but we wouldn't suddenly create, imagining going back to this idea of a standard deviation of 0, we wouldn't suddenly create, let's say, this 32, this standard deviation out of nothing. In this case, we just want to see, multiply this by this 1.8, this scale factor. Alright, so there's our answer in the end. Standard deviation is 16.2 degrees Fahrenheit. Alright, let's see what we can do. Let's go on. Alright. Kyung-yoon investigates the rate at which a cubical block of sugar dissolves in hot coffee. Initially, the cube has side lengths of 10 millimeters. This information is illustrated in the following diagrams. So here he's putting some sugar in some coffee, and here is our cube 10 by 10 by 10 millimeters. Kyung-yoon predicts that as the block of sugar dissolves, each side length will decrease at a constant rate of 0.2 millimeters per second. According to this model, find the length of one side of a block of sugar 20 seconds after it's placed in hot coffee. And part 2 asks us to find the volume of a block of sugar 20 seconds after it's placed in hot coffee. Alright, so let's write out a little equation just to kind of, I guess, work out part 1 of part A. So if we have this side length and it's equal to 10 millimeters, And it says we're losing 0.2 millimeters from this side length every single second. We could say 10 minus 0.2, and we're going to lose 0.2 in the first second, 0.2 in the second second, 0.2, another 0.2 in the third second, and this is going to occur at a constant rate. And so after 20 seconds, we'll have lost, well, 0.2, we'll have taken away negative 0.2 20 times. And in this case, we'll be left with 10 minus 0.2 times 20 is just going to be 4, and we're going to have a side length of 6 millimeters. Okay, so remember there's 3 marks here for 2-part question. So they're expecting to see some method somewhere. So here's part A. Let's go on to part 2. The volume of a block of sugar 20 seconds after it's placed in coffee. So this is a length of one side after 20 seconds. We know the volume of a cube. The volume of a cube is given by, in this case, length times width times height, and length times width times height are all equal. So really, it's just going to be side length times side length times side length, or side length cubed. And we know the side length after 20 seconds is going to be 6 millimeters. So the volume is equal to, well, 6 cubed. We can work that on our calculator, and it's going to be 216 millimeters, and this is, of course, going to be cubed units because it is volume. Okay. Pretty good. Let's go on. Let the function v of t represent the volume of the block of sugar in millimeters cubed t seconds after it's placed in hot coffee. Vt is given by, and then they give us some equation here, some function rather. Vt is equal to 100 minus 60t plus 1.2t squared minus 0.008t cubed. And they give us some domain. So this function applies from the first 0 second all the way up to the 50th second. So t is greater than or equal to 0, less than or equal to 50. 2-mark question here. They're asking us to find the first derivative. So find the derivative of this function here. I'm actually going to write this on the page just so I can look at this function at the same time. I'm going to write it right here. So I'm going to go ahead, Vt is equal to, I'm just going to write this function out, 100 minus 60t plus 1.2t squared minus 0.008t cubed. So 2-mark question, they're asking us to find the derivative. Okay, so how can we do this? And if we wanted to, actually, just similar notation, this is also dv over dt. Sometimes they'll give you this notation, but remember these two things, they mean the exact same thing. They're just two different ways of writing the derivative. This is change in volume, this d, change in volume over change in time. That's exactly what this function is, the derivative. Okay, so they're asking us to take the derivative. Remember, we have our power rule. I guess we can go there into our formula booklet. Let's go into calculus right here. And here is our power rule, the derivative of some function. And what is it saying again? It's saying if this is your function, take the exponent, multiply it out in front. So here is our n after we've multiplied it out in front. Then it says take away 1 from the exponent that we once had. So let's go back. And let's work that out. I'm actually just going to write that out here. I hope this isn't overkill, but here it is. So if we have some function, f of x is equal to x to the power of n, and we want to find the derivative of that function, what do? We take that exponent, multiply it out in front, so now it is nx, and then we look at this derivative, or sorry, this exponent rather. It used to be n, and now it is n minus 1. That is to say, we take 1 away from the exponent. Alright, so let's work that out here with this question. We start off with a constant. It's a little unusual because usually we have our highest degree term. That is to say, we have our cubes and our squares, and then we have our linear, and then just constants. But here they've rearranged it. It means essentially the same thing, but we're just going to have to be careful in terms of how we treat each of these terms, this 1, 2, 3, 4 terms. So here we have a constant to start off with this 1000. Remember, constants just fade away. They don't contribute to the slope at a point. This constant right here would just shift the graph up or down, and so it doesn't have any effect on the slope. So we can just essentially cross it off, and that is going to be 0 in terms of what it contributes. So we don't even really need to write it, but maybe we can. All right, let's go to the second term, this negative 60t. T is the same as t to the 1, and I guess if we want to use our power rule, we would take that 1, multiply it out in front, and we're going to have negative 60. And then t used to be raised to the power of 1, now it's raised to the power of 0, so t to the 0, or anything to the 0, is just going to be 1. So essentially we have negative 60 times 1, but we don't really need that. We can just write this as negative 60. Let's go on to our next term, and this should probably be a little more familiar now. Let's take this squared, so we see t raised to the power of 2, multiply it out in front. 1.2 times 2 gives us 2.4. T used to be raised to the power of 2, take 1 away, now it's t to the 1, which we can just leave. Let's go minus, follow along with this power rule here, 3, multiply it by the coefficient, this value that's out in front, this negative 0.008, and this is going to give us 0.081624 t. T used to be raised to the power of 3, take 1 away, and it's raised to the power of 2. So there is our derivative. Okay. Good. This is for part B. And let's continue on here. I'm going to actually clear up some space. I'm going to get rid of this power rule here. So part C asks us to find the rate of change of the volume of the block of sugar at t is equal to 20. So we have this function here, this v of t, which represents the volume of a block of sugar. And here, part C, they're asking us to find the rate of change of the volume of a block of sugar. So here's volume. Remember, the derivative gives us, this is what this notation, this dv dt, kind of shows us maybe more clearly. It says change in volume as a function of time, or yeah, this is exactly what it is. Change in volume as change in time. So the instantaneous rate of change, or the slope at a given point, that's what our derivative tells us. And so if we want to find the rate of change, that is to say the slope of this line, the change in volume at a given point in time, in this case after 20 seconds, we could just plug in this value of t is equal to 20 into our derivative right here. So let's go ahead and do that. Let's work that out for part C. So here is our derivative. V prime of t, it's going to be equal to, I'm actually going to rearrange it just to show you that the arrangement of the terms don't really matter. It doesn't affect things. It's still the same equation. So 0.24 t squared plus 2.4 t minus 60. And in this case, we want to find the instantaneous rate of change. So the rate of change of the volume when t is equal to 20. So if t is equal to 20, let's go ahead and substitute that in. For t, wherever we see t, let's substitute 20 in. 2.4 20 squared plus 2.4 times 20 minus 60. Okay, let's go ahead and put this in on the calculator. Here we go. So negative 0.024 24 times, watch your brackets in this case. I don't think we need that many brackets, but I guess it won't hurt. This is a little funny. I'm going to go back. negative 0.024. I see what it's asking. I typed in negative on the computer, but let's use it on the calculator. Times 20 squared plus 2.4 times 20 minus 60. Okay, make sure everything's good. 4 times 20. All right. So the answer in the end is 21.6. So what does that mean? It's losing 21.6 millimeters cubed every single second. That's a change in volume. Or sorry, that's the instantaneous rate of change. So at this moment, 20 seconds in, it is losing 21.6 millimeters cubed per second, we could say. All right, let's go back to the document and write that in. So negative 21.6. And if they asked us the units, it would be millimeters cubed for every single second. And we'll have a look at the mark scheme just to see. I don't think they... So this bracket means that it's not actually necessary to include the units here. Okay. All right, let's go on to part D. State one reason why the side length of a cube may not always decrease at a constant rate. And there are a few different reasons that we might imagine. It doesn't exactly say a mathematical reason, so we might just think of a real-world context. And one might be that if the temperature has something to do with the rate at which this sugar cube dissolves, we can't imagine necessarily that the temperature would remain constant. So that might be one possible explanation on why the cube, or the length of the cube, might not always decrease at a constant rate. So I'm going to go down here. So why might that not occur? Well, because temperature itself may not remain constant. And so if the length of time, or sorry, not the length of time, but the length of one of the side lengths, the rate at which these side lengths decrease depends in some sense on the temperature of the cube. If temperature isn't constant, then perhaps the rate at which this sugar cube dissolves might not be constant as well. I'm going to show you a few more examples. This is from the mark scheme right here. Let me just pull this up. So we have decreasing change in coughing temperature, the change in surface area of the cube. That's kind of interesting. So it gets smaller and smaller in terms of the overall exposure of the surface area, and so that might also influence the rate at which this sugar cube dissolves. Cube might break into pieces. Yeah, if we put a sugar cube in if we put a sugar cube in some hot coffee or some tea, it does break apart, and that would also influence the rate at which it dissolves. All right, and then here are some other examples. So what is a reasonable explanation? I guess that depends in some sense on the view of the examiner, but factors that would influence whether or not this sugar cube is going to decrease, or why might it not decrease at a constant rate. All right. Let's go on to question 10 right here. When studying big cats, researchers use a model in which the mass m kilograms of an animal is directly proportional to the cube of its shoulder height, h meters. A cheetah has a mass of 64 kilograms and a shoulder height of 0.8 meters. Part A asks us to use the model to find an expression for m in terms of h, and then part 2 asks us to find the mass of a different cheetah with a shoulder height of 0.75 meters. All right, so we're given a mass, we're given a height, and we want to somehow relate these two together with some kind of expression, or using some kind of expression, and then after that we want to use that equation in this case to find the mass of a different cheetah given its height. All right. So what is the way that we can relate these two variables together? There's one key piece of information, this key phrase here, which kind of gives us a big key to this question, and it's this directly proportional right here. So this directly proportional and directly proportional to the cube tells us what kind of question this is and what type of question. And just as a brief reminder, directly proportional relationships tell us that one variable is related to another. So in this case, this is a linear relation, or y is proportional to x. We can also have y is proportional to the square of x, or y is proportional to, like in this case, the cube of x. And it depends on these two key pieces of information. Not to maybe expand too much, but we have either direct or inverse variation. Since we're talking about direct variation, we're going to have this form where y is proportional to x. If we had inverse, I'll just write this really briefly because, yeah, it might show up as well. We would have this y is proportional to 1 over x. This would be y is inversely related to x, or y is inversely related to the square of x, and so on. In this case, we're dealing with direct proportion, so we actually don't need inverse, but these two key pieces of information, direct or inverse, and then to what degree. Is it just directly proportional? Is it directly proportional to, in this case, the square or the cube? This gives that other piece of information. So in this case, we're talking about it's directly proportional to the cube. Not to expand too much, but I guess we can kind of leave it like that. But so if we're talking about y is directly proportional to x, it's this linear relation. Y is directly proportional to the square. So an increase of one leads to an increase in the other by the square of that value. And then we have y is directly proportional to the cube of x, where an increase in one variable leads to an increase in the other by a cubic factor of whatever kind of increase we had. So I hope that wasn't too lengthy, but we're dealing with this y is directly proportional to the cube of x, or mass is directly proportional to the cube of the height. But we're not content to just say that, okay, they're related in some kind of way. We want to be more concrete, and in this case, we want to find a proportionality constant, the value of k. Proportionality constant which links these two values together. So this is what we're going to work with here. This y is equal to kx cubed. And with that, with this information which we're given, a certain mass right here and a certain height, we can go from having three unknowns, that is to say y, k, and x, to just having one unknown. We can find that proportionality constant. So let's go here and start off with a. So a1 right here. So we're dealing with this relationship. Y is directly proportional to the cube of x. In the context of this question, we're saying that mass is directly proportional to the cube of height. So we're saying mass is directly proportional to the cube of the height. Not just happy to say that there's a relation, we want to say, okay, well, what is that proportionality constant which links these two things together? So what is the k value in this case, the proportionality constant which links these two? So we know the mass, we know the cheetah. When a cheetah is 64 kilograms, its height is equal to 0.8 meters. So we want to take mass of 64, h of 0.8, sub these values into our m is equal to kh cubed, and then we can find the value of k. So we can end solve this, or just take 64 and then divide it by 0.8 cubed. I'm going to work that out on the calculator that I have beside me. 0.8 cubed, and then 64 divided by that. This gives us a value of k is equal to 125. So we now have an equation linking these values. So we have out of this, we have mass, oops, here we are. Mass, I'll write it in a different color even. Mass is equal to 125 h cubed. So now we've got a relation between mass and height. Part 2 asks us to find the mass of a different cheetah with a shoulder height of 0.75 meters. So we know its height. Can we find the mass? We can, because we've got an equation linking these two things together. So let's go ahead. Mass is equal to 125. This cheetah is 0.75 meters high, I guess from its shoulder height. We want to cube that value. and then let's go ahead and find out the mass. Again, I'm going to work it out on my calculator that I have here. 0.75 cubed times 125. This gives us a value of 52.734, so on, so on, so on. Let's go to 3 significant figures and say 52.7 kilograms. If we wanted to continue on here, it would be 375. But to 3 sig figs, 52.7. Okay, not bad. Alright, let's go on to the second part. Rubner's law states that the energy needs of an animal, E, are directly proportional to the square of h. The energy needs of a lion of mass 220 kilograms are k times the energy needs of a cheetah of mass 64 kilograms. Find the value of k. Alright, so this is admittedly, I think, a good challenge in terms of the question. So what are they asking us, and then how can we find it? They're telling us that the energy needs of an animal are directly proportional. Energy needs of an animal are directly proportional to the square of its height. Or if we wanted to, I guess we could say energy needs are equal to kh squared. So we've got some connection between the energy needs of an animal and its height. And they're asking us, if we have some 220 kilogram lion and we've got a 64 kilogram cheetah, and we know energy needs of an animal are proportional to its height, how many times greater are the energy needs of this lion than this cheetah of 64 kilograms? Alright, so in this case we can have the energy needs of the lion over, maybe let's use this for the cheetah, over the energy needs of the cheetah, and this should be equal to, and unfortunately we don't really want to overdetermine our variables, that is to say use k too much, but in this case they have a value of k. They're asking us, okay, well, how many times greater are the energy needs of a lion compared to the energy needs of the cheetah? So what we can do is find the energy needs of the lion, find the energy needs of the cheetah, and ask, okay, how many times greater is it? Alright, so let's go through this. First off, let's try to find EL over EC, or energy needs of the lion over energy needs of the cheetah. Energy needs of the cheetah, let's find that first. Energy needs of the cheetah are equal to kh squared, going off this right here, because that's what Rubner's law told us. Energy needs directly proportional to the square of h. So we know the height of the cheetah, that 64 kg cheetah. We know it had a height of 0.8 meters. So oftentimes IB questions, even in a paper 1, they'll link back to previous information. So here we know the height of this 64 kilogram cheetah. So let's find the energy needs of this cheetah. It equals to k, and then h, we said the cheetah was 0.8 squared. Let's work that out. 0.8 times 0.8 is 0.64 k. Alright. And unfortunately, we've got a k here and a k here. They mean different things. You don't want to write too many variables. Maybe for this question, I suppose, we can replace this k with an a. So AH, and 64a. And I think that will make things a little less confusing, I suppose. Let's find the energy needs of the lion. So we've got the energy needs of the cheetah right here. 0.64a, this something a. We don't know what it is, but since we don't need to know it in this case because we're dividing, it should be okay. Energy needs of the lion. Energy needs of the lion. Unfortunately, to find the energy needs, it's only in terms of height. And we don't know the height of the lion, we only know its mass. But we do have this equation right here, which links mass and height. So let's go and find the height of this lion, and then we can use that to find, well, we can use that to find the energy needs of the lion. So first off, let's go and find the height of the lion. We have this equation right here, which links these two variables together. So let's use that. So the mass of the line is 220. And the height of the line is what we want to find, h cubed. Now we can go ahead and end solve this. I'm going to work it out on my calculator right here. 220 divided by 125, and then we can take the cube of that value. And so the height of this line is going to be equal to 1.2074. I'm going to keep a few more significant figures, just because we're not yet at the end of the question, and by and large we want to keep as many sig figs as possible until we're finished. So we have the height of this line, 1.2074, or thereabouts. Let's find the energy needs of this line now. Energy needs of the line are equal to kh squared, or, oops, sorry, I know we used a here, so let's use a here as well. It's equal to a, and then the height of the line, 1.2074 squared. I'm going to work that out right here on the calculator that I have, 1.2074 squared, and this will give us a value of 1.458, and then a, because it's times a. Alright, so going back up here, we know the energy needs of the line in terms of A. We know the energy needs of the cheetah in terms of A. If we can find the energy needs of the line divided by energy needs of the cheetah, then we could see how many times greater it is. This is 0.64A. This is 1.458A. How many times greater is it? Let's go ahead and find out. So 1.458A over, in this case it is 0.64A, and this should give us the value of k. So I'm going to use my calculator that I have right beside me again. 1.458 divided by 0.64. This will give us a value of 2.278, or to 3 sig figs we can write it as 2.28. So how many times greater are the energy needs of this line compared to the cheetah? 2.28 times. Okay, quite a challenging question, I think, especially because there's a lot of links to earlier parts of the question. But a brief summary, if I can, I guess. Energy needs of a lion. Find the energy needs of the lion, the energy needs of the cheetah, and we're asked how many times greater is it. Energy needs of a lion cannot be directly found because we only have energy needs links to the height. Thankfully, they do give us the mass of this lion, and we can use that mass to find the height, and then we can use that height to find, well, the energy needs of the lion right here. And then after that, we can find out the energy needs of the lion in terms of some A, the cheetah in terms of some A, and since these are all proportional, we know that this is 1.458 A's, this is 0.64 A's, we can still say that it's 2.278 times as big, no matter what A is. We just know that it's 2.278 or 2.28 times as big. Alright. Okay, let's go on. Okay, question 11. The following diagram shows a semicircle with center O and a diameter PQ. So center O, diameter PQ. A rectangle OABC is also shown such that AB is equal to 8 and OA is equal to 5. Find the length of the arc BQ. Alright, so I actually like this question quite a bit. What are they asking us to solve? They're asking us to solve the length of this arc from B all the way to Q. Sometimes they can be kind of intimidating if it's just 5 marks and no context, but you just need to be more careful about process. Okay, so what is the arc length formula? I guess we can go to our formula booklet and find out. So let's go into geometry and trigonometry. Arc length formula, if you need to find it, is, I think it's further on right here. So the length of an arc is theta over 360 times 2 pi r. So essentially 2 pi r is the circumference, and then how much of that circumference do we have? 360 is the whole circle. What fraction of 360 do we have? So that tells us something. We're going to need to find an angle, and then we're going to need to find, well, the radius. Right? Okay, so first off, what is the radius of this circle? So we know the radius is just going to be the distance from the edge to the center, right? And where can we find that? Well, right here. And something might be kind of jumping out. Well, hey, this is a right angle triangle, and we should just be able to use the Pythagorean theorem to find r. There we go. That's our radius. So let's find r. We know that 5 squared plus 8 squared is equal to r squared. And we can end solve this. I'm going to use the calculator that I have right beside me again, because I think it's a little quicker. And I'll take the square root, and it would be the square root of 89 in this case. So r is equal to the square root of 89. We might want to leave it like that, just because it's more accurate. If we wanted a decimal approximation, since we're not yet at the end of the question, I would recommend you keep a fair number of digits. 4.334 is probably okay, but root 89 is more, what can we say? It's more accurate, I guess. Okay, now the next part, what fraction of this circle do we have? We're going to sweep all the way from here to here. In this case, we have this question, okay, well, what is this theta value here? And now it might be hard to find this directly, but if we know, for example, that angles on a line equal 180 degrees, if we can find this theta value, or let's call this maybe theta, let's call it maybe beta, I guess. Yeah, let's call it, it doesn't really matter so much. Let's call it beta right here. If we can find that angle, then we should be able to take 180 minus this angle, and then it will give us this red angle, this theta value right here. So, what do we have? We know that this is 5 right here, and this is 8 because it's a rectangle. We've got a right angle triangle, and we've got an opposite angle, and we've got an adjacent. So if you remember SOHCAHTOA, we've got opposite and adjacent. We're dealing with tan. Tan, in this case beta, is equal to opposite over adjacent. Let's fill in some of that now. Tan beta is equal to opposite of 5, adjacent of 8. Now we can go ahead and use tan inverse. Beta is equal to tan inverse 5 over 8. And that will allow us to solve it, but of course, if you want, you can also just end solve this, and then use something else besides beta, like x or something like that. All right, I'm actually going to work it out on the calculator here, just because I think it's always helpful. This degrees, make sure it's in degrees and not radians. All right, let's go tan inverse, and then we'll set up a fraction of 5 over 8. All right, 32 degrees, and I think that's pretty decent. 32 degrees is fine. Okay, let's go back to the document. Beta, we found out, was 32 degrees. Okay, so what is this value right here then? What is theta? Okay, we know that, I'm going to sweep up here if that's okay. We know that 180 degrees minus beta is equal to theta. Or another way we can put it is theta plus beta is equal to 180. But if a complete line is 180 degrees and we take away beta, well, we'll be left with this theta. All right. So 180 minus 32 is equal to our theta value. 180 minus 32 gives us 158. Sorry, 148. There we are. Okay, and to be honest, we're just about there. We know our arc length formula is arc length. Let's write it out as our arc length. Our arc length formula is equal to theta over 360 times 2 pi r. All right, so what angle do we rotate through here? We rotate through an angle of, we found this to be 148 degrees. Remember, this right here is 32 degrees and they sum to 100. So we have 148 over 360 times 2 pi, and then our radius, we can keep it as root 89. I think that's going to be the most accurate. All right, and let's go ahead and actually I'll work that on the calculator as well. All right, here we go. 148 over 360, and then this is all going to be multiplied by 2 pi, and then our radius was the square root, the square root of 89. And so our total arc length is 24.369. I'm going to write that out here. 24.369, or to 3 sig figs, 24.4. And what are our units again? Diameter A, circle, so the AB is, I guess it's just units. So 24.4 units is fine. All right, there we go. All right, final question here. Looks like it's a probability question. Zach raises funds for a library by running a game where players spin a needle. The final position of the needle results in an outcome where a player wins or loses money. The outcomes with associated probabilities are shown in the following diagram. So we have a 40% chance of winning $5, 10% chance of losing 8, and so on, so on. Let x represent the amount that a player of this game wins, and then part A asks us to find the expected value of x, and then part 2 asks us to interpret the answer here. Okay, so here we see 40% chance of winning 5, 10% chance of losing 8. We're not just going to add up the probabilities or anything like that. We want to, remember, for expected value, come up with something like a weighted average. And there actually is the formula in our formula booklet here. Let's go to probability. It looks a little confusing, but I think we can unpack it potentially, and it's not as bad. Here we are. Where are we? Right here. So the expected value of a discrete random variable. And this is actually the capital Greek S, or sigma. So we're talking about the sum of all independent events, where we begin at, well, the first all the way to the kth event, or the last event. We're taking the sum of all the events and multiplying the probability of occurrence times, well, the value, or the value in some sense that we could either win or lose. So when we're talking about this situation right here, we have a 40% chance of winning $5, 10% chance of losing $8. In this case, if we can sum up all of the probabilities multiplied by the return, then we would have in some sense a weighted average and our expected return. So let's go and write that out here. A1, we have E, the expected value of some event. And here we see we have a 40% chance of winning $5. So 0.4 times 5, plus we have a 10% chance of losing $8. So 0.1 or 0.10. 0.10, I'll write that out. And then we're going to potentially lose $8 in this situation. We have a 20% chance of losing $5. So plus 0.20, chance of losing $5. And then here as well we have, got a lot of chance of losing. Another 30% chance of losing $10. So 30% chance of losing $10. And if we were to sum all these values together, we would have something like a weighted average, and this would give us our expected return. So I'm going to work this out on the calculator, clear the screen here, and write this out. So 0.40 times 5 plus 0.10 times negative 8. I think I have to use the different negative right here, negative 8. Plus 0.20 times negative 5, and then lastly this 30% chance where we lose $10. Alright, overall we can expect to lose $2.8 on average. So I'm going to go back and write that out on the document. So negative 2.8. So interpret your answer to part A1. In this case, what does this mean? What does this negative 2.8 mean? It doesn't mean we're going to lose $2.8 every time, because sometimes we can actually win $5. Sometimes we're going to lose $8. We're never actually going to lose $2.8 on any spin, any individual spin, but overall, our long-term average return of playing this game is going to be negative $2.8. And that's what we can write here. So interpret your answer to part A is we have an average, this is an important word, average loss of $2.8, make a little more room for that, of $2.8 per game. And just to give you an idea of what the IB is expecting here, here's a mark scheme. Let's scroll down. So here we are. On average, players will lose $2.8. Players are more likely to lose $2.8. The key word is average, so do not accept players will lose $2.8 per game. Players are expected to win negative $2.8. Keyword is average, our long-term average. I guess this one is just too vague, I suppose. All right. So expected value does not equal 0, so the game is not fair. I think these are all, as long as we say that on average our losses are going to be this loss of $2.8 on average. All right, let's go on to this last part of the question. To encourage a person to keep playing this game, Zach increases the winning prize for the second game they play from $5 to $6. For each successive game they play, the winning prize continues to increase by $1. Emily plays K games. The kth game is fair. Alright. Encourage a person to keep playing this game. Zach increases the winning prize for the second game they play from $5 to $6. I see, okay. For each successive game they play, the winning prize continues to increase by $1. Emily plays K games. The kth game is fair. Okay. So right now, our expected return is negative $2.8. And our only way of winning is this $5 chance, this $5 return right here. But if we play again, let's say a second time, this turns to $6. And if we play a third time, it's loud. Whew. Okay, if we play a third time, this would increase to $7. And then a fourth time, this would increase to $8, and so on, till eventually this game is fair. So let's ask, or the question is, at what point on which game, the kth game, which game is fair? And we can use a little bit of trial and error, but we don't really need to in some sense. But to rephrase it, the question is, what does our winning have to be in order for the expected return to equal to 0? So I'm actually going to write that out. We know a game is fair when the expected value is equal to 0. And right now we have 0.40 times 5 but we want to know how much does it actually have to be. What does that return have to be? So that this value, our expected return, is equal to 0. Let me actually phrase that and write that as winning then, less ambiguous. What does that amount that we win have to be so that our expected value is equal to 0? So plus 0.10, this all stays the same. 0.20 minus 5 plus 0.30 negative 10. And we want the expected value itself to be 0. So this is all our expected value. We want to find how much do we need to win for this value right here, this $5 chance, this 40% chance that we have. It's not going to be 5. That's not going to make the game fair. What does that value have to be in order for this to equal 0? All right. So let's go ahead and put this into NSolve. I think I'm actually going to borrow some of this. I think I can actually, yeah. Menu, algebra, numerical solve. Actually, I'll do it right from the beginning. 0 is equal to, and then we can actually take this expected value as it is. 0.40 times x plus 0.10 to the negative 8 plus 0.2 plus 0.2 times negative 5, and so on. One last time, this is the 30% chance of losing $10. And all of this is what is known for certain. What is the value of x that is going to make the expected return equal to 0? So let's solve for x. And the answer is 12. So when x is equal to 12, this game is fair. So going back to the document for a sec, when this winning is not at $5, but when it's at $12, then this game is fair. So we're not quite done yet. We know that the winning itself has to be equal to $12. And we know that the first game you win 5, the second game is 6, and then at what point do we reach 12? So I'm actually going to set up a table just as a kind of way to stretch this out in some sense. So let's say this is the game, and then this is the winnings. On the fifth game, on the first game, we win 5. So if our winning is 12, well, we know this is plus 7. So 5 plus 7 is equal to 12. And we can do plus 7 here. And so it's not until the 8th game. Not until the 8th game is this game fair. So how can we write that out? The value of k must be equal to 8. Alright. Explain why Zach expects to raise money from the games Emily plays. Well, what can we say? One has to play. Well, how can we say this? If we just play one game, our expected return is going to be negative $2.8. So we can expect to lose $2.8 on average after the first game. On the second game, we're going to lose money. On the third game, we're going to lose money. The fourth, the fifth, the sixth game, we're going to lose money. It's not until, actually not until the 8th game. Not until the 8th game where we break even. The first 7 games, our expected return is less than 0. And it's not until, well, the 8th game that we actually start winning. So a way to represent this for B2, this is B1. For B2, we can say that the expected winning is less than 0 for games 1, 2, 7. That means we need to play a lot of games well, before we even start to break even. Alright, hope that was helpful. That's about it, and best of luck. Bye-bye.